Hello, everyone. My name is Xiaoyang. I'm a software engineer from Uber. Today, I'll be presenting with my teammate Tyler to talk about how we build scalable and performant CI system at Uber. First, we will go through the journey of our CI evolvement. Then we will talk about inspiring projects that we built in-house at Uber on top of Buildkite. In this section, I will use Uber's Go Monorepo as an example. Uber's Go Monorepo is the largest monolithic repository in the company, with over 500,000 files and over 3,000 engineers making over 1,000 commits a day. It definitely challenges us to answer an important question. How can we make code changes safely and fast? Luckily, we have Bazel to help us here. Bazel is our standard build system across the entire monorepo. It understands how each target is built and relates to each other. Then we can take advantage of this build graph to optimize our CI's behavior. For example, we don't need to validate everything if a developer only changes a README file. But we do need to be extra cautious if it changes a fundamental library that affects almost everyone else. Speaking of which, with a repository of this size, we don't want to just have a giant validation pipeline that does everything for every single change. Instead, we want to have different scenarios with different SLAs. For example, for some scenarios, we want to be stricter about the validation, but can be more tolerant about how long it takes. For others, we can forego some expensive tests and only focus on landing fast with running just certain critical tests. At Uber, every code change needs to go through a queue system. The queue would patch the change on the latest head of the main branch and run some validations to make sure that the change is safe at current tip of the repo. The queue, however, is not linear. It doesn't just blindly validate change by change then push. That would be too slow. In order to speed things up, it speculates all possible scenarios of the tip of the main branch. And when head actually changes, it invalidates certain scenarios. For example, if A succeeds and is pushed, then it means B and C need to land on top of A. Then we don't need to care about these builds anymore. But if A fails, it will never land to main as is. Then these builds are not valid anymore. Also, it's possible that A, B, C are just completely independent. For example, each of them just changes a different README file in a different directory. Then it doesn't really matter who ends first. But things can get a little complicated if they touch some overlapping targets and form some kind of graph relationship like this, especially when there are many other changes during rush hour. The queue would need to be smart enough to choose how to speculate and what to build. If you're interested, you can learn more about our queue system in this blog here. Anyways, as a result, the system induced intensive CI traffic, invoking many builds and canceling many builds at the same time. This is our landing queue CI traffic graph by hour. And you can see that if we're not careful, then this amount of CI build traffic can cause serious congestion of the queue. In the old times, we were just using plain old Jenkins, which executes a bunch of scripts in order. You can see that all of this is very linear. We can configure some common plugins and runtime configuration steps based on exit codes, but there's nothing much we can do beyond that. All the logs are skewed together, and scrolling pages of these is just not fun. On top of that, we did have to maintain the Jenkins cluster itself, which can sometimes break. This is how a classic flow of our CI jobs look like. Initially, we also did try some sharding strategy on Jenkins and parallelizing some steps, but only to an extent. It worked at first, but it involves making a lot of hacks in the bash script, and we could not change anything confidently without breaking anything else. Quickly, this became a pain point for us. Also, it's not flexible enough to change the sharding strategy or add more parallel steps. Last but not least, Jenkins stores logs on machines and rotates them over time, meaning the logs will be gone eventually. Otherwise, it will eat up the disks. So we wouldn't have anything to look at if we want to, say, debug a test from a month ago. Now we're on Buildkite. From the first look, you can see that this is a total different experience for us. Not only do we have a clear, full picture of what's going on, it's also fast. This one that we're looking at here, this one builds the entire Monorepo in just under 25 minutes. And you can also see that this build is speculated based off of other code changes. So it's pretty complex. And we can take advantage of the logging group features to organize the output, making it much more user-friendly. And we can come back anytime to look at this log because it stays here forever. Now let's take a closer look at the build. First, instead of a giant set of steps running in order, we take advantage of Buildkite's steps generation mechanism and build our CIs dynamically simply by just running Buildkite agent pipeline upload. Here, the main step is the entry point of everything. It runs our in-house build changed targets calculation algorithm to compute what basal targets are changed. And based on that, we trigger many different steps. Some of them will run in parallel, and some of them will just wait for dependencies. And some informational steps like this one are just soft fail and not blocking. And we also upload dependent artifacts such as tracing profiles, error logs for debugging purpose, and other files for inter-steps communication purposes. For example, sharding. Each of these this steps is heavily sharded, as you can see, and each of these shards reads targets to build or test by downloading corresponding artifacts. This is super easy to use. We no longer have to pass around variables in Bash with complex string manipulation tricks. And we can use different sharding strategies for different kinds of targets, such as changing sharding size or sending them off to different queues. Additionally, we can also annotate the builds with internal links, so users can quickly go back to code review, for example. And all of this logic is wrapped up in a single script that invokes our new programmatic CI runner, which is written in Golang. Unlike Bash, now we can easily extend the steps by simply adding Go functions and write unit tests for each of them. We also built our in-house shadow service using Buildkite's webhook events. The service listens to build start events or finished events from a pipeline and triggers or cancels builds in another pipeline based on the configuration, which is also readable from Buildkite's API. This way, we can have production pipeline and shadow pipeline side by side. This comes handy when we want to test features like rolling out new versions of plugins. Now let's talk about performance. During the migration, one of the things that we were hoping for the most was containerized CI. This means each Monorepo team has more control over their CI environments and is more isolated from operations like upgrading the machine fleet or upgrading operating systems, etc. When we rolled out Buildkite initially, we used the Docker container plugin that comes for free from the Buildkite open source community. It simply starts with Docker container on the host, runs the scripts, which runs Bazel, which starts the Bazel server and does all the fancy work, then exits. Upon exit, the plugin also tears down the container, which means the Bazel server is gone too, and we lose all the memory footprint. Then the next run kicks in, everything starts all over again. This happens to every single run for every agent on every host, and that's a lot of overhead. Not only does it need to pull the image and build a container and start it, it also runs Bazel's on the cold server, which is surprisingly slow. Even if we mounted some on-disk cache directories to share across runs, still Bazel query slowness quickly became a bottleneck and made it not so much faster than Jenkins. But what if we don't terminate the container? What if we just leave it running and make the subsequent scripts reuse the same container if certain conditions are met? The Bazel server will remain running and ready to respond to next request until terminated. We can do this for other containers too. But now with this many containers running and not terminated, how does each job choose which one to run scripts in? We solve this by assigning each container a hash sum and a bunch of labels based on many factors, such as pipeline name, agent ID, composer files, content, certain environment variables. This script can now use the same information to uniquely locate the container and execute there. So when we do, now when do we actually recycle the container? The answer is we just take advantage of Buildkite agent's lifecycle. Since multiple Buildkite agents rotate on the same host, whenever we see a new agent come up, we're sure that the old agent is dead and cannot dispatch or accept new jobs, regardless of pipelines. So we can terminate all running containers and start new ones. This orchestration works pretty well for us so far. It shows about 30% performance gains for basal queries, and it keeps the container long enough to be warm and not too long to be stale. Meanwhile, we also mount a set of static on-disk cache directories to share across containers. These caches are read-only. We also have another Buildkite job periodically refresh these cache and upload them to some remote storage. Then the first job running on the host will download it, and later jobs can just reuse it. On the other hand, we also have a Basal remote cache service running. This serves as an extra layer of cache for sharing Basal build outputs and further boosts the performance of our CI jobs. You can read more about the above here in this blog. And now I'm going to hand off to Tyler to talk about some of our most interesting projects inspired by Buildkite.
Hi, everyone. My name's Tyler French, and I work on Uber's Go developer experience team, along with Xiaoyang. And today, I'm going to talk about some of the additional things we've done alongside and with Buildkite to make it the best experience at Uber. So first, I'm going to talk about metrics and alerting. Let's start with looking at the story of a runaway build. Well, here we have a build, and it started at some point. Everything is looking good so far, but what happens is the build gets stuck somewhere. And then it gets stuck somewhere, and it keeps going, and we hit a latency violation. So we probably should have alerted on this. We probably want to know when something goes wrong. But unfortunately, the job will keep going until it times out. And then we have a metric reported of a build duration, in this case, a build failure. And then we have an alert that sees this duration, sees it's above a threshold, and then fires an alert. So in this situation, we have a lot of lost time. So Buildkite does this with push metrics. So push metrics are a service itself emitting a metric every time an event happens. So in this case, a build finishes. That's the event. It tells us this is how long it took and other information about it. Now, here's another side, pull metrics. This is where we have a separate system that looks at the service, looks at Buildkite, and checks in on it, sees how it's doing. And this is much better for real-time analysis. This is things like checking how many builds are running at one point, checking what an agent is doing, checking which jobs are taking the longest, what is happening right now. And so we designed the Buildkite prober. So imagine we have Buildkite over here on the right running on EC2 instance. We designed a service that is on-prem, isolated from Buildkite, and it periodically probes Buildkite APIs. So in our case, we probe every minute, we analyze the responses, and then we report to the users. So this is reporting to users directly, dashboards, reporting to metrics and alerting systems, and also reporting to a database. We probably want to store this information and see if something happens like it in the future. This also gives us a little bit more availability for in the future. If we want to extend this to parsing logs or looking at artifacts, we can add these things to the same system using this API probing. Additionally, we're able to see if the API goes down. So it's very, very good for increased visibility in the state of Buildkite. So here's an example of the number of active jobs running in our CI validation pipeline. As you can see, at one point it goes up to 90. Maybe we should have an alert there. Maybe that's a lot. We get more insight into these information. So here is the news story of a long build. The build starts, the build gets stuck somewhere, but then when we hit that latency violation, we have an alert fire immediately because there is a build that has been running longer than a threshold. And we don't have to wait for the job to time out. We can have our on-call start acting immediately, and this saves us a lot of time. So here is an example of what we were just discussing. This is the live step duration for Buildkite. So it shows us what steps are taking what amount of time. And we can see that, for example, in the middle, the build test step is taking a long time, and we can take action on that. And that step is probably still running. So it's good to be able to look at these things live rather than wait for them to finish. Another useful part of this probing service is we can check in on bad agents. So one side of checking hardware is you can go into the hardware and actually see if it looks good. But that's pretty complicated, and it's actually pretty difficult because there's so many different things that could be bad. There's so many different things to check, and there's a lot of edge cases. So instead, we can just look how many jobs have recently failed on this agent. And statistically, if there's a lot of sequential failures in a row, then it's probably a bad host. So let's say this step fails here. That may pass a threshold that we've set of sequential failures we allow, and then we can just take the agent out of rotation and cancel those steps, restart them on new hosts. And this is very important for keeping our fleet healthy, and we're able to identify problems like this quickly and quickly fix them. Here's an example of us probing these agents. As you can see, a lot of agents fail 3 times in a row, but very few fail 4 times in a row. And even fewer fail 5 times in a row. And as it goes up, we're very sure that this is an actual agent we need to take out of rotation. Now I want to talk about user-defined jobs. So user-defined jobs are jobs that people have come to us and they want help setting up a job of any sort. So it could be a periodic job, could be a post-land job running on every commit, could be a CI job running when you create a code change, could even be an ad hoc job that users run from their command line. But the problem is that we don't want to create 200, 300 different pipelines for all these use cases. Instead, we want to do stuff in one place. So we designed a domain-specific language for extensible CI. How this works is we have a config file in YAML that a user creates. They create a command that's just a script, and then this is run through a config parser, which, as part of our pipeline, is then uploaded as a dynamic step. So let's look into this a little more. So we have one pipeline called GoCodeUDJ, which has the same entry point every time, the runner. And the runner is the only static piece of code. It is the only definition of this pipeline that works for 200, 300 different uses. And here, what we do is we pass in the config file as an environment variable, and then the job will use the runner to parse the config and upload dynamic steps based on what the user wants to do. And so here you can see that it runs their job in a separate step. And an important thing here is Buildkite makes it very easy for us to look up our job specifically. So I don't want to see every single user-defined job that's being run. I just want to see the one that I made. So we can use the metadata and add a job key and then say, oh, we want just my job. And then we immediately can only filter out our jobs, see which ones have passed and failed. And we can even use this with the Buildkite API to check in on things. Lastly, I want to talk about dependency management, specifically Go, but mostly just at Uber. So in our Go monorepo, we have 2,000 plus third-party dependencies, which it's a lot. So they get stale. Not everyone's upgrading their dependencies. A lot of them are unowned. Maybe the teams have left Uber. Maybe it's something that someone brought on, they forgot about. A lot of them are unhealthy. This could just be it's someone's small repo that's not very well maintained, or it could be a vulnerability. And then lastly, it's very slow to upgrade 2,000 dependencies actively. So the only reasonable answer here is we have to automate. So how do we automate dependencies and their upgrades with Buildkite? Well, imagine we have a bunch of dependencies. We send that list to Buildkite, and then we talk to some version registry. So we use Go proxy for Go. There's GitHub, there's Maven for Java and for anything on GitHub. And if we get new versions, we can create sharded upgrade jobs. And the great thing about Buildkite sharding is that each job shard is on its own checkout of the repo. So when we make 200 concurrent code changes, we only take like 5 minutes, and we can create 200 dependency upgrades in a very short amount of time. And the more important thing here is a lot of times dependency upgrades require a lot of compute power and a lot of caching. For example, Go mod tidy takes a lot of network requests to download all the repos. But here we can share that cache across the upgrades, and it actually becomes very fast to make all these changes. So now we have these upgrades. They create code changes. These are all ready to land, except it looks like one of them failed. So this is important stateful information that's kind of hard to use. So we also created a database, and we're able to keep information about what upgrades have failed, which ones passed. We assign tasks based on these automated upgrades. It gives us a much more useful way of controlling our third-party dependencies. We can also have a user initiate their own upgrade by using the remote code changes with Buildkite. So we've created a command line interface where someone says, oh, I want to upgrade Golang X crypto. That will start a Buildkite job from the greenkeeping endpoint, as we call it. And then this will auto-generate the code change. And then the user can land the code change. And they've created their upgrade much faster and much easier than if they would have done the code change locally on their own. That's all for today. I want to thank everyone for listening in. And I hope you learned something. And if you're interested in joining Uber, follow this link here. And also, if you have any questions, please don't hesitate to reach out to me or Xiaoyang. Thank you.